Good day, I'm Norman Wildberger. This is a series on the foundations of mathematics, and currently we're investigating elementary calculus from the point of view of polynomials or polynumbers. This is a novel and much simplified approach to the subject. In our last video we had a look at linear and quadratic polynomials or polynumbers and their associated graphs. And today we're going to carry on talking especially about parabolas or quadratic polynomials in more detail. So let's summarize what we accomplished in the last few slides of the last video. Alright, we're talking about a quadratic polynumber or polynomial. There it is there, p equals just a list of numbers a, b, and c. Or in standard alpha form, a plus b alpha plus c alpha squared. And we're assuming this is really a quadratic polynomial so that this term here, this c constant, is actually non-zero. So it really is of degree 2. And we discovered by expanding the Taylor bipoly that the first derivative or the first subderivative was b plus 2c alpha. And the second subderivative was c. We also determined that the tangent line, or the first tangent, to the polynumber at the point r is given by this expression. So that's a line, a degree 1 polynumber, at least most of the time, unless this is 0, which is an approximation to the polynumber p at the point r. R is just some random number. And we're generally working over the rational numbers here, but a lot of what we say works for the integers as well. Okay, at this point we can observe something reasonably interesting, that the slope of the tangent line to p at r is exactly the derivative of p evaluated at r. So we saw last time that when we had a line like this, that the two constants here had geometrical significance, that this was the y-intercept and this was the slope. And this quantity here, b plus 2cr, is exactly what you get when you take the derivative and you evaluate it at r. So this gives us a geometrical interpretation of what the derivative, or the first subderivative, means. It is the slope of the tangent line to the polynumber or polynomial at the point r. So for different points r, there are different tangent lines, and those tangent lines will have different slopes, and the slope at every point r is given by the derivative. A useful deduction to make from that is this theorem here, that the tangent line is horizontal precisely when r has the value minus b over 2c. Now that's an immediate consequence of setting the derivative, which is b plus 2cr, equal to 0, and solving for what r must be. This is a linear equation, so when we set it equal to 0, we are guaranteed to have a solution. It's minus b over 2c. This number is, as we'll see, very important in terms of the geometry of the parabola, or the quadratic polynumber. And we can see that another way by doing something that we've already talked about in a former video in this series. If you look at MathFoundations 48b, we talked about completing the square in a quadratic expression. We're going to do that now with this quadratic polynumber p, a plus b alpha plus c alpha squared. And I must warn you that our notation here is different from what it was there. This is a sort of a non-standard notation. We're indexing our coefficients with a, the constant term, and c, the coefficient of alpha squared. Alright, so what we're going to do is we're going to rewrite this thing here, first of all by taking out a common factor c, which we're assuming is non-zero, writing it as c times alpha squared plus b over c times alpha plus a over c. And then in this expression here, we're going to add this term and also subtract it so that nothing actually has changed. Where did this term come from? Well, it's exactly half of this coefficient here. So we're taking half of this coefficient here and squaring it, and then also subtracting it as well. The reason why we're doing that is because now these first three terms here are actually a perfect square. This thing here is c times alpha plus beta over 2c squared. And the reason is simply that when we square this, we're going to get alpha squared, we're going to get b over 2c squared, and twice the product will give us b over c times alpha, the thing that's right there. Of course, there's also the other terms. When we take them outside the bracket, multiply c by a over c, we get a. And when we multiply it by minus b squared over 4c squared, we get minus b squared over 4c. And I'll write that just a little bit more compactly by taking this constant business over a common denominator, 4c. So we get 4ac minus b squared all over 4c as the constant term there, and c times alpha plus b over 2c all squared there. And now we make a simple but important observation that whenever we have a square, that square is necessarily positive. When I say positive, I generally mean greater than or equal to 0. So this term here, if we substitute alpha for r, any number, then r plus b over 2c all squared will always be positive. So I've repeated that formula that we've just obtained. We've rewritten the polynomial p in this fashion here. So it's the same polynomial, it's just been rewritten. And now we're going to deduce some important things. So we'll put these together in a theorem, 3 different statements. The first is that if c is positive, then p of r is bigger than or equal to this number for any r. With equality happening here, precisely when r happens to be minus b over 2c. So this is an inequality. If there was an equal sign, it would be an equality. And when we have an inequality like this, it's telling us this is always bigger than or equal to this, it's usually interesting to ask, well, what about the special case? When exactly are they actually equal? Because that's included here as a possibility. So this second part of the statement is telling us that the equality occurs precisely when r has this value. Let's just have a look at that statement first. That's an immediate consequence of this, because if c is positive, then this is positive, and we've just observed that this quantity here is always positive. So this is a positive thing. And so if we add it to this, we're always going to get something which is bigger than or equal to this. That's the statement there. The value of the polynumber or the polynomial at r is always at least this number here. And when do we actually get equality? Well, we get equality when this term is actually equal to 0. And this will be equal to 0 precisely when the value r here satisfies r plus b over 2c equals 0. In other words, when r equals minus b over 2c. That's illustrated by this picture here. Okay, so here's a picture of such a quadratic polynomial where c is positive. So it opens up like this. We say it's a parabola opening upwards. And here is the value minus b over 2c. The function's value at that will be exactly this, because this term will be 0. So there's the value 4ac minus b squared over 4c right there. And geometrically, you can also see that the parabola is opening up. It's always bigger than or equal to this value, and it attains this value exactly when x equals this number here. That's what we're saying. And this number here is exactly the same quantity that appeared in our previous theorem, which stated that this tangent line here, the tangent to the polynomial at this point, is horizontal. So it's a standard kind of important fact in calculus that we have a minimum here. The minimum is characterized by the tangent being horizontal. That's what we're seeing here. So the second part of the theorem is what happens when c is strictly negative, if c is less than 0. then the claim is that P of R is less than or equal to this quantity for any R. And again, equality happens exactly in the same situation when R equals minus B over 2C. And that's again a consequence of this formula, because if this term here is now negative, less than 0, and this is always positive, then the product will still be negative. And so we're always get here as a total something which is less than or equal to this, because it's this plus something negative, so it's always going down. And it doesn't go down, we have equality precisely when this is 0, and that's the same condition as previously when R is minus B over 2C. So the picture that goes with that is this one here. It's a parabola opening downwards. There's the critical point minus B over 2C. At that point, right there, the value of the polynomial is 4ac minus b squared over 4c, and for all other values it's something less. The value is less. And again, that's the place where the tangent is horizontal. The slope is 0. And there's a third part of this theorem, that the line x equals minus b over 2c is an axis of symmetry of the parabola. So in this picture here, what we're talking about is this line here, the line where x happens to be this critical value, or over here, this line here. And the claim is that it's an axis of symmetry, and that means that if you take any point on the parabola here and you reflect it on equal amount on this side over here, you still get a point on the parabola, and conversely. So it's like a mirror. If you put a mirror here, then the parabola would be reflected on itself. So it's completely symmetrical in that line. It's called an axis of symmetry. And why is that? Well, it's again because of this expression here. That if you take any point where you add r to the coordinates, so if you have some value x here, so that you're adding r to minus b over 2c, then this quantity here will just be r. On the other hand, if you go r in the opposite direction, then this quantity will be minus r. And the reason why the two values are the same is because r squared and minus r squared are equal. That's the reason why the curve is symmetrical about this line. All right, so this is a very nice and important formula in the study of the geometry of a parabola or a quadratic polynomial. There's another very interesting and important consequence to this basic formula that we've established. There's the polynomial p, and there it's rewritten after having completed the square. So the consequence of this is that we can actually say something about what the shape of such a graph is. Okay, the point is that the graph of p, or a graph of p perhaps we should say, because there's no unique graph, it can be obtained from the graph of q equals alpha squared. This is the simplest quadratic polynomial, by doing three things. By first scaling in the y direction by some constant c, actually the same c here as here, then translating by b over 2c to the left, and then by translating up by 4ac minus b squared over 4c. So why is that? Well, suppose we take the polynomial alpha squared. If we, perhaps that's right there. Picture it right there. That's the standard parabola. Usually y equals x squared in xy terms. And it goes through the point 1, 1. It goes to the point 2, 4. Of course, it goes to the point 0, 0. It's symmetric along the y-axis. That's your basic parabola. So if we take that thing and we scale it by multiplying it by c, what happens? Well, of course, it depends on what c is. Okay, but let's say c happens to be, say, 2. Okay, so that means that when instead of plotting 1, 1, we would plot 1, 2. Instead of plotting 2, 4, we would plot 2, 8, and so on. So all the y coordinates would be multiplied by 2. The parabola would then look more constrained, like this, but it would be basically rescaling of this one. Okay, so that's one step. Scaling, multiplying by c has this effect. On the other hand, if c happened to be, say, between 0 and 1, then the effect would be sort of the opposite. It would be more like going from here to here. The parabola would become wider. And if c was negative, well, they would have then again yet a different aspect, because then you'd be multiplying by -1. So the parabola, instead of opening upwards like this, would be opening downwards like this. That's the effect of multiplying by -1. So after that rescaling, then what happens if we replace alpha with alpha plus b over 2c? Well, the effect is that instead of having the thing centered here at 0, it's now moved over to be centered at minus b over 2c. So, for example, if b over 2c happened to be positive, then we would be moving in this direction here. And why is that? So the probably simplest way of seeing that is, ask yourself, what happens if we evaluate this as at minus b over 2c? If we evaluate this at minus b over 2c, then we get 0, then we get just the same thing as we get if we evaluated this at 0. So this thing evaluated there is the same as this thing evaluated there. So it means that the whole thing is shifted over so that its vertex is now at this point. Of course, this quantity doesn't have to be here. It could be on the right-hand side. It could be anywhere along the axis. Okay, it's starting to look a lot like our formula. Now we just have to do one more thing. We have to add this, but this is some number that's independent of r. And the effect of it is simply to take the values and add this number to them. So this number was 5, for example. Then the graph would just be obtained from taking this and adding 5 to the y-coordinates of all the points. So it would effectively just move it up 5. Or if this was minus 3, the effect would be to subtract 3 from all the y-coordinates, so the effect would be to move it down 3. So here I've shown it sort of moving up by a certain amount. All right, so that's a proof of this claim. And what it tells us is that all parabolas more or less have the same shape. Well, in the sense that the only real difference between the shape of the graphs is going from here to here in this rescaling. So we're rescaling it, making it wider or narrower, and perhaps flipping it over. But then after that, we're not really doing anything to the shape. We're moving it around, translating it, but not changing its shape. So all quadratic polynomials have graphs which are readily identifiable. Right? You know what a parabola looks like. The story with cubics and quartics and higher polynumbers is much different. And that's going to be a very interesting aspect. It's an interesting question in algebraic geometry of what those things look like. But like lines are pretty predictable, parabolas are also very predictable, which is good. So to clarify those translates and scalings on the last slide, let's have a look at an example. So here is the polynomial that we've looked at before, 5 minus 3 alpha minus 4 alpha squared. And here I'm going through the process of completing the square just so you can see how it looks again in a specific case. First I take the minus 4 out as a common factor. So I get alpha squared plus 3 over 4 alpha minus 5 over 4 because I've taken a minus 4 out. And then in here I look at this term here and divide it by 2 to get 3/8, and I square it and add it. And to keep things the same, I also have to subtract it as well. Then these three terms here together form alpha plus 3/8 squared. And these two terms here, well, when we multiply by minus 4, this thing here becomes just 5. And this one here is 9 over 64. If we multiply that by 4, we get 9 over 16. With a plus sign because there's a minus there and a minus there. So when we simplify, we get minus 4 over alpha plus 3/8 all squared plus 89 over 16. Okay, so how could we graph that? From the point of view of starting with your basic parabola alpha squared. Now here I've drawn a more standard kind of diagram where I've actually plotted points. So this is the point 1, 1, point 2, 4, point 3, 9, minus 1, 1, minus 2, 4, minus 3, 9. There's our standard parabola, a graph of it. Admittedly not a very refined graph, but a graph nevertheless. All right, and let's do these various steps. First step is to multiply by -4. So what effect does that have? Well, each of these points is multiplied by -4, in the sense that the y-coordinate is multiplied by -4. So instead of plotting 1, 1, we're going to plot 1 minus 4. And instead of plotting 2, 4, we're going to plot 2 minus 16. And instead of plotting 3, 9, we're going to plot 3 minus 36. But that's off our page, so we can't see it. So we just get these few points, and we connect them up. And then that's our graph of -4 alpha squared. Next thing we have to do is to take care of this shift in here. We're replacing alpha with alpha plus 3 over 8. So what does that do to this thing? Well, it moves it over to the left. It's a translate to the left. Okay, there's a plus sign, so you might get confused and think, oh, we're moving it to the right. No, we're moving it to the left. The graph here is to the left. And it's now got its vertex at -3/8. And in your mind, you can check that because the value at -3/8, namely here, is going to be 0. So it really does go through that point there. And otherwise, we just take all of these points and move them over by -3/8 to get that one there. And then the final stage is to add 89 over 16, which is just a little bit more than 5. So we have to add a little bit more than 5 to each one of these points. And we obtain this graph. That's our graph of the original polynomial p. Illustrating how it comes from alpha squared by a sequence of transformations, a scaling, then a horizontal translation, then a vertical translation. Now we're going to have a few more slightly advanced theorems, which are often not found in high school courses or even in first year, second year courses at uni or college. It's a bit of a shame because these are natural, easy to prove consequences of what we've already done, and I think they're geometrically interesting facts about parabolas. All right, the first one is that if we look at tangents to a general parabola or general quadratic polynomial, and those tangents are at R1 and R2, then the two tangents will meet at a point. And here is an explicit formula for where they meet. So we'll have a look at the formula and then we'll talk about some very interesting aspect of it. Okay. So what we're claiming is that if we look at the two tangent lines to P at R1 and R2. So here they were. These are the formulas that we had before, with R1 for the first one and with R2 for the second one. Those are the two equations of the lines, and we have to find where they meet. So we have to use the meet of lines theorem, which is a formula that tells us if we have equations for the two lines or linear polynumbers, then what is the point which lies on them both. So the formula for that meet is this minus this over this minus this. All right, what is this minus this? Well, the a's cancel, and we get CR2 squared minus CR1 squared. And what is this minus this? Well, now the b's cancel, and we get 2CR2 minus 2CR1. And the second term, the second coefficient, is this thing times this one, there it is there, minus this times this, all over that same denominator that we had before, this minus this. Okay, so then what you do is you expand these two terms out, and it turns out that the numerators in both cases have a factor of CR2 minus R1, which you can cancel. And this thing here becomes R1 plus R2 over 2, and then you can check, it's an exercise, that when you do the expansion and divide by the common factor, you can get A plus B R1 plus R2 over 2 plus C R1 R2. Now, the interesting point that answers an exercise that I gave you in the last video. In the last video I asked you to explain this phenomena that two tangents were meeting above their midpoint. And here what we see is this is a very general phenomena that the x-coordinate of the meet of these two tangents is always exactly halfway between the two coordinates. In other words, it's the average. And I should remark about this thing here, it's also rather pleasant. It has the same form as the original polynomial, a plus b something plus c something else. And this is a linear thing and this is a quadratic thing, just like over here. But here we've got the average of the two r's, and here we have the product of the two r's. So in some sense it's almost the simplest kind of thing that you could cook up with r1 and r2 sort of involved in here. We're going to need one more result about lines that we didn't talk about last time. So this is the theorem that tells us how to find the equation of a line between 2 points in terms of polynomials. So if x1 and x2 are distinct, then the line p equals a plus b alpha, in other words the linear polynomial on which both x1, y1 and x2, y2 lie, is given by these two equations. So this is the expression for a and this is the expression for b. And they have very similar forms as the formula we were just using. The formula for a is x1 y2 minus x2 y1 divided by x1 minus x2. And b is y1 minus y2 over x1 minus x2. So I remind you these two numbers represent the y-intercept of the line as well as the slope of the line. So this is a relatively familiar formula for the slope of the line between 2 points. This is perhaps a somewhat less familiar formula for the y-intercept of the line between 2 points. So what's the proof? Well, we have to solve two equations. We are trying to find a plus b so that this point and this point both lie on this linear polynomial. In other words, y1 equals a plus bx1 and y2 equals a plus bx2. We have to solve these two linear equations for a and b. That's a relatively easy exercise. I'll leave you to do that to find that those are the solutions. So we're going to apply that formula that we've just proven to have a look at the standard parabola. Parabola p equals alpha squared, or in x and y coordinates, y equals x squared. So there it is there. I've drawn it a little bit freehand this time. It goes to the point 1, 1, to the point 2, 4. It's a very beautiful curve. And we've chosen 2 points on it, a1 and a2. And the x-coordinate here is r1, and the x-coordinate here is r2. So this point is the point r1, r1 squared. And this is the point r2, r2 squared. And I'm interested in two things. I'm interested in the line that joins those 2 points. And I'm also interested in the two tangents to the parabola at those 2 points and where they meet. So we know where they meet because we've just proven a theorem about that. And I remind you that they meet at, first of all, the x-coordinate is the average of r1 and r2. And the y-coordinate here is obtained from the polynumber by taking a plus b times this plus c times the product of r1, r2. Well, this is a very simple form. It only has the sort of the c term, and the c is 1. So we're only getting r1, r2 instead of those 3 things added up. So this is the formula for the point where the two tangents to the curve at a1 and a2 meet. And I remark once again that the x-coordinate here is exactly halfway between r1 and r2 because it's the average. All right, what about the equation of this line? Well, we've just proven a formula for that. So here are the 2 points. Then let's say we say that the line is s plus t alpha. Then the formula that we just wrote down was that s is equal to, how do you get that? r1 times r2 squared minus r2 times r1 squared all over r1 minus r2. So here there's a common factor of r1, r2, and the other factor is r2 minus r1, which cancels with r1 minus r2, leaving a minus sign. So s is minus r1, r2. And what about t, the slope? It's r1 squared minus r2 squared divided by r1 minus r2. Well, that factors immediately as r1 plus r2. And so there is the equation for our line. Minus r1 r2 plus r1 plus r2 all times alpha. Now, it's a very pleasant relationship, the relationship between this line and this point. Okay. And in more advanced mathematics, and we'll be talking a little bit more about this, this is a very, very important relationship that somehow characterizes this conic. Okay? So if we move these 2 points around, then of course this line will move around, and this point here will also move around. And we say that the relationship between this line L and this point L is an example of polarity. So we sometimes say that this is the pole of this line, and we sometimes say that this line is the polar of this point. We'll talk a little bit more about that in future videos. That's an important concept, so you're seeing it here for the first time in this simple case of this parabola. There's a few more things to point out here. One is that given this parabola, we can in some sense find addition and multiplication geometrically inside here. So how is that? Well, suppose that you have 2 points, r1 and r2, on the line, and you wanted to add them. Well, one way of getting that sum, r1 plus r2, would be to take r1 and r2, take the points on the parabola, draw this line, and look at its slope. Right? We know that r1 plus r2 is the slope of this line. So the addition, it's maybe a curious way of thinking about it, the addition can be sort of done geometrically if you can read off the slope. What about the product? Well, you can see a product here. Okay, if you wanted to find what r1 times r2 was, one way of doing that would be to say, all right, we can take r1, r2, we can look at the 2 tangents, and we can see where they meet, and then the y-coordinate of that is going to be r1 times r2. Another way of finding the product is to look at this equation here. There's a product floating around here. And what is the significance of this quantity? It's the y-intercept of this line. So here's a kind of a curious sort of slide rule, a parabolic slide rule for multiplication. You want to multiply r1 times r2, you just go up to the parabola, you draw the line, you see where that line meets the y-axis. That's, well, not exactly the product, it's minus the product. Okay? So here, in this case here, the product of this one times this one is pretty close to being minus 2. So both addition and multiplication are somehow encoded in the geometry of the parabola. Well, worth thinking about these two things, and I'll give you now some exercises so you can have some practice thinking about this lovely geometry. So the first exercise is very much in line with what I've just been talking about. It's another way of thinking about addition using the geometry of this standard parabola. So I want you to show that if we're talking about the standard parabola, p equals alpha squared, there it is there. And if you have 2 points on it, just as before, a1 and a2 now up here, with coordinate r1 here and coordinate r2 here. And let's just denote the vertex by O for origin. That's got coordinate 0, 0. Then, if you do the following, if you take the line through the origin, which is parallel to a1, a2, okay, that's the meaning of this. It's parallel to here. It means it has the same slope. Okay, then you find out where it meets the parabola in the second point. Then that x-coordinate there will be r1 plus r2. It's another way of geometrically adding 2 numbers using the geometry of the parabola. This second exercise is a very lovely and important fact, that if A lies on the polar of B, then B lies on the polar of A. Okay, so here's a general parabola. It doesn't need to be the standard parabola. This works for a general parabola. So you have a parabola here, and you have a point A. And that point A has polar line, this one here. And I remind you what that means is that if you draw the tangents to the parabola at the places where the line meets it, you get to A. So that's the polar of A. And there's another point B, and here in green is its polar. So if you take the places where the green line meets the parabola and draw the tangents, you get there. Okay, the statement is that if A lies on the polar of B, which in this case it does, then B lies on the polar of A. It's a general fact. You can prove it just for the standard parabola. Those of you with a bit more algebraic skills can try to see if you can do it for a general parabola. Excellent exercise. And the third exercise relates, again, a chord of the parabola and the meet of the two tangents down here. So if this point here is x-coordinate r1 and this point has x-coordinate r2, then we know that where these two tangents meet, that's going to have x-coordinate r1 plus r2 over 2, the average of r1 and r2, the place halfway between them. And now the exercise is to have a look at the corresponding point on the parabola with the same x-coordinate. So you just go vertically up or down till you hit the parabola, you get a point. And the claim is that if you look at the tangent line at that point, it's going to be parallel to the line joining A1 and A2. This is not necessarily horizontal, right? It could be anywhere depending on the chord A1, A2. All right, those are three excellent exercises that will get you really appreciating the geometry of the parabola. And I hope starting to appreciate the fact that we're doing mathematics here, we're doing calculus. And even though our origins were very elementary, it seemed as if we did almost no work, and suddenly calculus popped up in front of us. This should be disorienting to mathematics educators. If you're a mathematics educator out there, have a think about this. Have a good long think about it. Next time, we're going to go up a step to talking about cubics. And we're going to apply our reasoning about tangents and derivatives to study cubic equations, which are a fabulous world of all kinds of interesting things about cubics. We're going to make some contact with that. I'm going to show you the prettiest theorem that I know in calculus. And you will not have seen it before, so it will be a real treat. All right, so next time, the prettiest theorem in calculus and cubics. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.